Center limit theorem. Often, it becomes necessary to study characteristics that do not follow the normal distribution. The central limit theorem relates to situations where other distributions are involved. Let us get started. Theorem 1. If x1, x2, xk up to xn is a random sample of size n drawn from a population with mu and sigma, then x bar, the mean of the sample, can be approximated as a normal distribution with parameters mu and sigma by square root n, provided n is very large. Note, the above result does not make any assumption about the distribution from which the data is drawn. Thus, even if the distribution is positively or negatively skewed, the result holds. The sample mean, x bar, still follows the normal distribution. The result is fairly accurate when n exceeds or equals 30. Thus, in example 7.4, the results are valid even when the population does not follow the normal distribution. Data on certain characteristics, however, are discrete rather than continuous. For example, each item in a lot may be classified as defective or non-defective. A quality executive may be interested in estimating the proportion of defectives in the lot, based on a study of a sample of items. The distribution of the sample proportion is highlighted in another version of the central limit theorem, which is as follows. Now let us look at Theorem 2. Suppose P is the proportion of defectives in a lot. Let P bar denote the proportion of defectives in a sample of size n. When n is large, P bar follows the normal distribution with mean P and standard deviation square root P multiplied by 1 minus P by n. Note, as seen earlier, the above result is fairly accurate when the sample size exceeds or equals 30. The result is valid even if the study relates to other qualitative characteristics such as ripe and unripe mangoes.